Hello and welcome. Today, we're diving into a really cool and fundamental problem in science. How in the world do you measure things you can't actually see? Things like stress or motivation or intelligence. Let's pull back the curtain on the secret toolkit behavioral scientists use to measure the unmeasurable. All right, let's just jump right in with a question for you. How would you scientifically measure stress? And I don't mean just saying, oh, I feel super stressed out. I mean, how would you put a hard number on it? So you could, say, compare my stress level to yours in a research study. It's way trickier than it sounds, right? And you know what? Stress is just the tip of the iceberg. Behavioral science is absolutely full of these huge, important, but totally intangible ideas. We talk about motivation, self-esteem, intelligence, hunger, exhaustion, all the time. We all know these things are real, but you can't exactly measure self-esteem with a tape measure. So how do researchers get around this? Well, they've got a system, a process for taking these fuzzy, abstract feelings and turning them into cold, hard data. Let's walk through how they actually do it. Okay, first things first. Scientists need a proper name for these invisible ideas, and the official term is a construct. A construct is just a concept that we can't point to or see directly, but we assume it exists because it helps us explain why people do what they do. Think of it as the official scientific label for something like anxiety. So you've named your invisible concept. Now what? This is where the magic happens. Scientists create something called an operational definition, and this is the absolute key. It's the specific, concrete, real-world procedure they're going to use to measure that unseen thing. Basically, you're defining the concept by the operation you use to measure it. Let's make this real. Imagine a hypothesis, like overexertion leads to exhaustion. I mean, it sounds true, but overexertion and exhaustion are super vague. An operational definition fixes that. You could say, okay, for this study, we are defining overexertion as working more than 12 hours, period. And exhaustion is defined as extreme tiredness and an inability to work more. See? All of a sudden, we've gone from a fuzzy idea to something we can actually observe and count. Okay, so we've got our definition. Overexertion is working more than 12 hours. Simple enough. But hold on a second. Is that actually a good definition? Does that really capture what we mean by overexertion for everyone? And this leads to the next huge question every single researcher has to obsess over. Is my measurement any good? To figure that out, there are two, let's call them golden rules of measurement. Every single scientific measurement has to pass these two tests. You've probably heard these words before, but we're going to see what they really mean in a research context. And they are reliability and validity. Let's start with the first one, reliability. This is all about consistency. The question here is pretty simple. If I use my measurement over and over and over again, under the exact same conditions, do I get the same stable result every time? This target analogy is perfect for this. Just look at the top left target for a second. See how all the shots are clustered tightly together? That's reliability. It's consistent. Now, don't worry that they're nowhere near the bullseye yet. That's a different problem. For now, the key is that the measurement is dependable. It gives you the same result time after time. And that brings us to the second golden rule, which is arguably even more important. This is validity. This is the accuracy check. The question here isn't just, is it consistent? It's, okay, it's consistent, but is it consistently measuring the right thing? Does my measurement actually measure what I claim it's measuring? This slide puts it all together beautifully. On the left, we've got what we just saw, reliability without validity. The shots are consistent, but consistently wrong. The next target over, that's a mess. It's neither reliable nor valid. The shots are just all over the place. But the target on the far right, that is the scientific bullseye. The shots are tightly packed right in the center. That is both reliable and valid, consistent and accurate. That's the goal. So let's just hammer this home. Reliability asks, are the results consistent? It's hitting the same spot on the target every time. Validity asks, do the results satisfy the objective? It's about hitting the bullseye. You absolutely need both for a good measurement. And here's the kicker. You can't have validity if your measure isn't reliable to begin with. Think about it. How can you be accurate if your shots are landing in a different place every time? And just for fun, here's a perfect example of what a lack of validity looks like. The mood ring. According to this chart, the color might mean you're feeling road rage or hungry for waffles.
Or maybe you just have a full bladder. A mood ring might be reliable. It consistently changes color based on your skin temperature, but it is absolutely 100% not a valid measure of your mood.
So how do scientists check for validity in a serious way? Well, one of the key methods is to see if their new measurement correlates with other well-established measures of the same thing. In these charts, called scatter plots, if the dots show a consistent pattern, like a line going up or down in graph A or B, that's a really good sign. It suggests the two measures are related, which is great evidence for validity. But if it looks like graph C, just a random cloud of dots, there's no relationship and the validity is very, very questionable.
Now, even when scientists know all these rules, they have their constructs, their operational definitions, they're checking for reliability and validity, getting good data in the messy real world is incredibly hard. There are just so many potential pitfalls that can trip them up.
First off, there are just simple sources of error that can make measurements less reliable. You've got observer error. I mean, we're all human. People make mistakes recording data. The environment itself can change. Maybe the room gets a little hotter or noisier during the study. And of course, the participants themselves change. People get tired, they lose focus, their mood shifts. All of this just adds noise to the data.
But then there are the even trickier problems, the human factors that can threaten a study's validity. There's something called experimenter bias, where a researcher's own expectations might subconsciously influence the results. Then there's reactivity. This one is huge. People just act differently because they know they're being observed. And finally, you have demand characteristics, which is when participants guess what the study's about and then change their behavior, either to help the researcher out or maybe even to sabotage the results.
So, what's the big takeaway here? Measurement is hard. It requires so much care and critical thinking. The next time you see a headline that says, "Scientists prove X," I want you to ask yourself, how exactly did they measure X? Was their measurement reliable? And most importantly, was it valid? Knowing these rules gives you a powerful new lens for understanding the science that shapes our world.